Warm up for lesson 5-3. Pause to do the problem. And here's the answer. Pause. And here's the answer. Don't forget to put in the missing terms in your synthetic division. Pause. So here's an application of synthetic division. We're using the area, trying to isolate the height, and when we want to divide the binomial into the trinomial, we use synthetic division. Pause. A similar problem to the last one. This time the formula is volume is equal to the area of the base times the height, and we are going to divide by the binomial, and we're going to use synthetic division to do that. Lesson 5-3, polynomial functions. Objective: to evaluate a polynomial function, identify general shapes of graphs of polynomial functions. Okay, a polynomial in one variable is an expression of this form. So you're going to have x's to powers, and they all have to be integers, and you can have some numbers being multiplied in front of it, and you are adding and subtracting all of these terms. This is written in standard form because we're going from the largest value to the smallest value. So here is an example of some polynomials, and I also want to introduce a new word called leading coefficient. So for a constant, that's the degree 0, because x to the 0 power, since there are no x's, and the leading coefficient is 12. For a linear, you're looking for the highest power of x, which is x to the first degree, and the number being multiplied to that x to the first degree is 4. We call that the leading coefficient. Quadratic, the degree is 2, that's the highest power, and the number being multiplied to the x squared is 5, and so on. All right, so let's go ahead and practice some problems. In this problem, we notice that the highest degree here is to the 5th. So we say the greatest exponent is 5. That means it's degree 5. And the leading coefficient is always the number that's being multiplied to that, and that's going to be 8. B is not a polynomial one variable because we're timesing x times y, so we don't talk about anything else there. Here, notice that this is not in order, it's not in standard form, so you have to look for the highest power, and the highest power is 8 right here, and the number being multiplied to that x to the 8th is -4. So let's go ahead and practice with these problems. Is this a polynomial one variable? And the answer is no, and that's because this does not make it a polynomial. We have to have x to positive powers, not x to the -1 power. Over here, the polynomial is a one variable. The answer is yes, and we look for the highest power right here, so it's a degree 6, and the leading coefficient is 5. Over here, be careful, it's located right here. So this is a polynomial one variable. The degree is 6, and the leading coefficient is -1. Your turn, pause, and do the problems, and here are the answers. Let's talk about a polynomial is a continuous function. Continuous means that there's no breaks in it, that it's just a smooth curve. This example right here is, because it's to the 3rd degree, we call it a cubic polynomial function. The simplest polynomial function is one with only one term. A and B are non-zero, and these are called power functions. And if you know the element of in the polynomial, in the domain of the polynomial function, you can find the corresponding range. So we'll start talking about domain and range again. Let's take a look at evaluating a polynomial. I want you to notice that here is the polynomial function. The numbers being multiplied are decimals, that's okay, but all our exponents are positive powers. All right, looks like we want to evaluate it at 1.5, so we're going to put 1.5. Everywhere there's an x, we're going to write 1.5, and we're going to put it in our calculator, and we're going to get this answer. Now this represents, it looks like the volume is in liters, so I labeled it liters. Pause and see if you can do this problem, and here's the answer. Let's take a look at evaluating function values of variables. So instead of putting in a number, we are going to put in an expression. So we're going to put in an expression into our function. So what we want to do is replace the x in our function. We want to replace it with whatever we're trying to substitute. So right here is what we want to substitute into this function. So wherever there's an x, and there's an x here and here, and we're going to replace it with a 3c minus 4, 3c minus 4. And when we get that, we're going to multiply it out and we're going to simplify. So this portion represents this part right here. Now let's represent the 5c. So everywhere there's an x, we are going to replace it with a c. And don't forget that this is 5 times f of c, so we're going to have to multiply the 5 to each one of these. And we're going to get this expression. Now we're going to put them together. We're going to put this expression that we got up here, it's right here, and we are now going to subtract this expression that we got over here. We're going to simplify and get this answer. Okay, let's go ahead and I'm going to do it one more time with you. Here's the expression we're trying to get, and we're trying to evaluate g of this. So here's our g right here, and everywhere you see an x, I've put a parentheses. I put a parentheses plus x. So this green part is going to be what it's going to be represented by this g of f of a minus 2. All right, plus 3, and then I'm going to put a brackets because now I'm going to do g of 2a, which means everywhere there's an x, I'm going to put a parentheses and a parentheses. And this purple part is going to represent g of 2a. Okay, so let's go ahead and do the problem. I'm actually going to substitute. Wherever there's an x, I'm going to write 5a minus 2. And then I'm going to write 5a minus 2. And this is going to replace this x, and that's going to replace that x plus 8. So this whole thing represents what I have in this green right here. Now I'm going to go to purple, and I have my 3 here, and everywhere I see an x, I'm going to write 2a. So I see an x here, I'm going to write 2a, and then I'm going to write 2a here. All right, so now I'm going to go into my black, and I'm just going to multiply things out. 5a minus 2 squared means this. And then I'm going to start distributing. So that's minus 25a, and distribute. That's plus 10 plus 8 plus 3. Now I'm going to keep this in brackets here. And I'm going to multiply this out. That's going to be 4a squared minus 10a plus 8. I'm going to continue to multiply. I'm going to do my foiling, which is 25a squared. I'm going to do my outer, which is minus 10a, my inner minus 10a, my last plus 4. Then I'm going to have this minus 25a, and I have plus 10 plus 8, and now I'm going to distribute, plus 12a squared minus 30a plus 24. Okay, so now there are no parentheses, and I'm going to start gathering up like terms. Okay, this is a like term with this. So that answer is going to be 37a squared. Now I'm going to start collecting a's here, and it looks like I have some here. So this is going to be, all of them end up being negative. So I have negative 20 here, a negative 10 and a negative 10, a negative 25, and then I have a negative 30. So that's going to be a 5, 7, negative 75. So this is negative 75a. Now I'm going to collect all of the numbers, and that'll be here, and here, and here, and here. And these numbers all appear to be positive. So this is going to be 14, 14, and 8 make 22. And then I have a 24. So this is going to be plus 46. So now we have found the value of this expression. All right, your turn. Pause, and here's the answer. And again, I just wrote the problem out. Everywhere I saw a b, I put a parentheses. squared plus 3, and then minus 2, and again I just put a parentheses for my b squared plus 3. So this told me to substitute that in, which I did, and I substitute x in over here. I multiplied everything out, and then I got my answer. Let's take a look at the graphs of polynomial functions. A constant function looks like this. It's a horizontal line. A linear function, degree 1, has some kind of slope. Quadratic could parabola going down or parabola going up. Cubic has this characteristic. One end is going in one direction and the other end is going in the other direction. Quartic, degree 4, has the look of that the ends are going to go in the same direction. Over here they went in different directions, just like linear went in different directions. The quintic is going to go into different directions as well. So let's take a closer look at all of those, and let's talk about what we call end behavior. All right, this function is an even function. How do I know that? Well, it's to the second power. It's our quartic. So as x goes to negative infinity, so I'm going to put a little arrow, as x goes to negative infinity, I want you to notice that the y's are going up. So we say that the y's are going to positive infinity. Now let's do x approaches positive infinity. So as x gets larger, I want you to know that the y's are getting larger, and so that's going to positive infinity. This is an example of an even function. The domain is all real numbers, and the range will always be greater or equal to the minimum. So whatever this value is, the range will be above that as well. Let's take a look at an odd function. How do I know it's an odd function? And the way I know that is that it's to the third power. And let's take a look at what happens as x approaches negative infinity. So I'm going to, as x goes in this direction, look at the y's. The y's are going down, so we say it's negative infinity. Now let's switch and let's x go to positive infinity. As x gets larger, it looks like the y's are getting larger too. So this is positive infinity. Notice that their end behavior are going in opposite directions, where their end behavior here we're going in the same direction. The domain is all real numbers, and the range will be all real numbers because we're approaching either infinity. Let's take a look at another even function, but this time the leading coefficient is negative. So it's an even function, and the leading coefficient is negative. Now when this was a parabola, the parabola would face down. This is a quartic, and notice that it's going in the same direction. Let's go ahead and do the same thing. We're going to allow x to go to negative infinity, and notice that y is going to negative infinity. All right, now let's switch and let x go to positive infinity, and notice that the y's are going to negative infinity. Again, they're going in the same direction. Domain is all real numbers, and the range will be all numbers less than or equal to this maximum value. Let's take a look at this odd function. I know it's an odd function to the fifth power, but the leading coefficient is also negative. Now let's go ahead and let x go to negative infinity. So as x goes to negative infinity, notice that the y's are going up, so that's positive infinity. Let's switch. As x goes to positive infinity, let's look at the y's. The y's are going to negative infinity. So again, they're going in opposite directions. The domain is all real numbers, and the range will be all real numbers as well. All right, so odd degree functions will have an odd number of real zeros, 1, 2, 3, or 1. Even degree functions will always have an even number of real zeros, and a zero real number. So here's an even, and notice it has 0, and here's one that has 4. Okay, let's take a look at, I'm going to be giving you pictures, and I want to see if you can describe the behavior by looking at the picture. Okay, so the first thing is we're going to take a look as x approaches negative infinity. So I'm going to start right here. As x goes to negative infinity, I want you to notice that the y's are going down, so we say negative infinity. Now I'm going to switch and I'm going to let x go to positive infinity. And as x goes to positive infinity, look at the y's are going to negative infinity. So since the end behavior is the same direction, notice they're the same, then we can say this is an even function. And the graph intersects the x-axis in 2 points. So there are 2 real zeros. Let's do this same kind of problem. We're going to allow x to go to negative infinity, and we're noticing the y's are increasing, so that's positive infinity. Now we're going to take a look as x goes to positive infinity. Notice that the y's are going down, so that's negative infinity. When the end behavior is different, we know that it's an odd function, and in this case it intersected at 5 points, so there are 5 real zeros. All right, so let's do it again. Here's a picture. Let's see if we can describe what's going on. I'm going to go to negative infinity, and when I go to negative infinity, it looks like I'm going up, so that's positive. As x is going to positive infinity, it looks like the y's are going lower, so that's negative infinity. Notice they are different, so it's an odd function. And how many zeros? Well, you look at how many times it crossed the x-axis, and that is 3. Let's do it again. We're going to allow x to go to negative infinity. Notice that the y's are going negative, so that's negative infinity. Now let's look at positive. As x approaches positive infinity, it looks like the y's are also going down. Now since they're the same, we know this is an even function, and the number of zeros, how many cross the x-axis, is 2. Okay, your turn. Stop the screencast, and here's the answer. Stop the screencast, and here's the answer.